Hi everyone, I'm Dan Fullerton, and today I'd like to talk to you about vectors and scalars. Our goals are going to be to learn to differentiate between vector and scalar quantities, to use scaled diagrams to represent and manipulate vectors. We want to be able to determine x and y components of vectors, and also go the other direction and given x and y components of vectors, be able to find the angle of a vector. So to begin with, let's talk about scalars. Scalars are physical quantities that have a magnitude or a size only. Things like temperature doesn't have a direction, it only has a size. Mass, how much stuff you're made up of in kilograms, doesn't have a direction associated with it. Or time, which we measure in seconds. And you may think of time going forward and backward, but that's not really a direction like a direction on the compass. So those are all scalar quantities. Compared to those, we also have vectors. These are quantities that have a magnitude and a direction. Things like velocity. I'm going 35 meters per second due south. Things like force. I'm pushing on something with a force of 50 newtons, and I'm pushing in a specific direction. Or momentum. That truck coming at me, barreling at me down the highway, has a tremendous momentum, and the direction of that momentum is right toward me. Now, we typically represent vectors in physics as arrows, and the direction of the arrow, of course, tells you the direction of the vector. And the longer the arrow, the bigger the vector. So the light blue vector here, let's call that vector A, has about half the magnitude of vector B. Vector B has the same direction as vector A. It's twice as long, therefore it has twice the magnitude. If we assume, for example, that vector A represents a force of 10 newtons, and I go and measure that with my ruler, I find that it's actually 4 centimeters long from tip to tail. Therefore, this must be telling me that there are 10 newtons over 4 centimeters, or every centimeter is roughly 2.5 newtons. So if I then go and I measure vector B with my ruler, I find that it is 8 centimeters in length. So what force would vector B represent? Well, 8 centimeters times 2.5 newtons per centimeter tells me that vector B has a force of 20 newtons, which makes sense. We said it was twice as big as vector A. If vector A is 10 newtons, vector B should be twice as big, 20 newtons. So we can use vectors in scaled diagrams to help us figure out exactly what magnitude of a quantity we're talking about. Now, adding vectors is a fairly straightforward process. Graphically, here we have two vectors, a yellow vector and a light blue vector. If we want to add them, what's really nice about vectors is you're allowed to move them around. You can't change their direction or their length, but you can slide them wherever you want. So the trick to adding vectors is to always line up all your vectors so that they are tip to tail. So if we slide these around and make these tip to tail, our light blue vector now moves so that its tail is touching the tip of the yellow vector. Now our next step is if we draw a line from the starting point of our first vector to the ending point of our last vector, we get our answer. The sum of vectors A and B is this vector in black, A plus B, which we could determine graphically. And it doesn't really matter in what order you place the vectors. We could do the yellow one, then the blue one, or the blue one and the yellow one. For example, if we went with the blue one and the yellow one, you can see we still get the exact same answer. We just went in the opposite order. And that will work for any number of vectors, from 2 vectors up to 200 vectors, and further on. Line up all your vectors tip to tail, draw a line from the starting point of the first to the ending point of the last, and you will end up with the sum of your vectors, vector addition. And you call the sum of any vectors the resultant vector. So in this case, our black vector is our resultant vector. Vector subtraction is almost as easy. If we think of algebraically adding two values, a plus b equals c, well, if we want to subtract them, a minus b is equivalent to writing a plus negative b. So if this is vector a and this is vector b, how do we get negative b? We just switch the direction of the vector. Now we have a and negative b. The light blue vector is now pointing in the opposite direction. So we have a plus negative b, which is the same as a minus b. Now it's an addition problem where we're adding a and negative b. How do we add vectors? We line them up tip to tail. So let's slide this a vector over here so that it's lined up tip to tail with negative b. And then we can draw a line from the starting point of our first vector to the ending point of our last vector to give us our answer, this black vector. Straightforward. Once again, basic vector manipulation. Now when we're talking about vectors, oftentimes you have vectors at an angle, and if we draw this on an xy axis, we can label the angle between the horizontal axis and our vector as angle theta. Well, there are many times in physics where we can make our life much simpler if we only work in one dimension at a time. So we could think of this gray vector as actually being comprised of the addition of two smaller vectors. One vector, which travels here along the horizontal axis, we will call the x component of the vector. The other component is the vertical component. And if we add those two, you can see that our gray vector is the resultant of our two yellow vectors, our two vector components which lie only along a single axis. This is our x component of vector A. This is our y component of vector A. And we can use basic trigonometry to figure out exactly how big those component vectors are. Ax, because it's the adjacent side, is going to be equal to the magnitude of vector A times the cosine of angle theta. The y component of our vector, ay, is going to be equal to a, and because now we're talking about the side of the right triangle that is opposite angle theta, that's going to be a sine theta. And you could actually go in the other direction too. If you happen to know ay and ax, or any two of those three sides, you could always go and find that angle using trig too. For example, if we knew the vector components ax and ay and wanted to find theta, we know that the tangent of theta is the opposite side, ay, over the adjacent side, ax. Therefore, angle theta would be the inverse tangent of ay over ax. Let's take a look at an example. If a soccer player kicks a ball with an initial velocity of 10 meters per second at an angle of 30 degrees above the horizontal, find the horizontal and vertical components of the ball's velocity. Well, let's draw our axes here first. There's our y-axis and our x-axis. And the soccer player kicks the ball with an initial velocity, so there's our initial velocity vector. We'll call that vi for initial velocity, which has a magnitude of 10 meters per second, and it's at an angle of 30 degrees above the horizontal. We want to find its horizontal and vertical components. Well, to find its horizontal component here, ax, that's going to be a cos theta, or 10 meters per second. Notice that I'm substituting in with units, 10 meters per second, times the cosine of 30 degrees. I plug that into my calculator and I get something right around 8.7 meters per second. So we found its horizontal component. Now let's see if we can't find its vertical component. Ay, its vertical component, will be a sine theta. Once again, I substitute in with units, 10 meters per second, sine 30 degrees, or 5 meters per second. And if we look at this, just to see if this makes sense, we can see that our x component is bigger than our y. That makes sense. The green vector on our drawing is bigger than the orange vector. And we could even check this out using the Pythagorean theorem. A squared plus b squared equals our hypotenuse squared, right? So if we took 8.7 squared, added it to 5 squared, we should come up with 10 squared, which would be 100. Looking at another example, here we're talking about an airplane that flies with a velocity of 750 kilometers per hour at an angle 30 degrees south of east. What's the magnitude of the plane's eastward velocity? Well, let's start off with the diagram. If we draw our axes, our compass, there's north, south, west, and east. Its velocity is 750 kilometers per hour, but it's 30 degrees south of east. So if we start east and go 30 degrees south, that angle must be 30 degrees, and this must be 750 kilometers per hour. We want to find the magnitude of the plane's eastward velocity. Well, if we want its eastward velocity, we want this component here along the x-axis. That's its eastward component. So we're looking for ax, which must be a cosine theta, because that's the adjacent side of our triangle, or 750 kilometers per hour times the cosine of 30 degrees. Plug that into my calculator. Should get something close to 650 kilometers per hour. Let's take a look at yet another one. Here we have a dog walking a lady, a very excited dog, at about a distance of 8 meters due north. I guess that would be a displacement, a change in position with direction. So the dog walks our lady 8 meters due north, and then 6 meters due east. 8 meters north, 6 meters due east. Determine the magnitude of the dog's total displacement. Well, to do that, this looks like a vector addition problem. We start at our starting point. Our vectors are already lined up tip to tail, so we go from the starting point of our first to the ending point of our last. That red vector must be our dog's total displacement. How do we figure out how big that is? Well, we could use the Pythagorean theorem, because that's a right triangle. A squared plus b squared equals our hypotenuse squared, or 8 meters squared plus 6 meters squared equals our hypotenuse squared, or 100 square meters equals our hypotenuse squared. Take the square root of both sides, and we find out our hypotenuse, or total displacement, must be 10 meters. Now, we've talked about the resultant vector being the sum of two or more vectors. Let's talk about the equilibrant vector. The equilibrant vector is the opposite of the resultant. To find an equilibrant vector, all we do is we find the resultant first, and then we switch its direction. So if you had a problem like this where it says the diagram below represents two concurrent forces. Concurrent just means they're happening at the same place at the same time. Draw the equilibrant force vector. Well, to find the equilibrant, let's first find the resultant. These aren't lined up tip to tail, so I'm going to redraw my vectors so that they are lined up tip to tail. And to find the resultant, I start by drawing a vector from the starting point of the first to the ending point of the last. Now, because I don't want the resultant, I want the equilibrant, all I do is I switch the direction of that vector. Right now, my resultant is pointing in that sort of northeast direction. So if I want the equilibrant, I need to switch its direction. My equilibrant vector must look something like this. There's my answer. So, next steps. In your house or backyard, define a starting point and an ending point somewhere in your yard or in your house. Then, find 3 vectors that if you followed all 3 vectors would get you from your starting point to the ending point. And make sure you write those down with their size, how far, and their direction. Then try rearranging those three vectors and see if you get to the same point each time. Does that work? And can you explain why or why not? If you need any extra help, check out aplusphysics.com. Thanks and have